Well, now in this part, this is the last part about the GAN architecture. And the thing that we want to do, we want to just go over a few famous GAN architectures. I'm not going to break that down for you, like what exactly is happening inside the architecture, because that is probably not interesting at all, and you can simply read it online. The point is that I want to just give you a bit, just throw you some names to your mind so that just in case you wanted to check something, you have access. I mean, you have something in the background. And the papers to all of, I mean, the original papers are somehow cited in here, but they are also available on the course page. So you can check, you just go in the further read list and then read those papers if you're interested. So one of the very primary GAN architectures, which somehow did work quite well, was a kind of CNN-based architecture. So the generator was a CNN, and it was eventually using just convolutional neural networks to start from a say 100-dimensional latent space, so 100-dimensional IID Gaussian variables generate samples generated, and then we pass it through these different layers of convolution to just build up some tensors, and we end up with a 64 by 64 three-channel tensor, and that was supposed to be an RGB image, right? So you start from latent space, do some convolution, you end up here. So this is our Z, this is X, and then for discriminator, they were doing just a basic MLP discriminator or just a basic CNN discriminator, first layer convolution, then one MLP, and then they do the classification. And here they use just vanilla GAN to train. And yeah, this was, I mean, you see that this is by no means a sophisticated architecture, but this was very able to just generate what we expected. So these are the samples you see from the output of this deep convolutional GAN, DC GAN. Usually we call it DC GAN. So you see the outputs, and they are at that point of time where we had very hard time to generate meaningful samples. They were quite something. Now, this was one thing. Then in 2018, so they came up with StyleGAN. And StyleGAN was a kind of, more sophisticated kind of architecture. This was one of the architecture which somehow made a sort of, breakthrough. Everybody was having like look at StyleGAN, how uh, original and real the outputs are. So in the StyleGAN architecture, what we do, we generate a latent sample, and then we first go through, a bunch of fully connected layers. So we're going to generate, process it a lot into the case where we have a sort of, decomposed form of latent. Like every single part of latent now supposedly is just going to help us generate some part of the image that we want to generate. And now you're going to inject all of these different parts into this uh, different style networks, they call it, which is eventually just a bunch of convolutional layers. And then each of them are going to generate a part of the image, right? So you're going to say, okay, I want an image of a cat, and then the eyes should be of this form, somehow like this, right? So you're going to start with generating some, rough idea of cat, and then focusing whether the eyes are angry or happy, and so on, right? And gradually you're going to style it till it get the output. Again, at that point of time, this was quite something, but if you read the paper through, you're going to see that the architecture is not that crazy large, but it was able to generate very high quality images. So they had two versions of StyleGAN, and finally, like the high quality samples are of this form. And some of them, when you focus on them, you start to see that they are like generated images, but still, I mean, for the given time, it was a kind of huge breakthrough. Now, the next idea was that people started to see a StyleGAN is working. Everything is based on, convolutional layers. Now, it says that if we go very, very deep, we're going to get much better outputs. And if you don't want to go deep with convolution, as you might have it in the deep learning course, if you remember from deep learning course, we're always going to have the issue with vanishing gradient, and we need to get rid of this, meaning that we're going to add some skip connections or residual units. So they started to put residual units with skip connections as the blocks which are building or data samples from the latent. So the latent is some Gaussian sample again, and it's going to be processed with multiple residual blocks. This is going to help us having, a sort of much deeper network, because we don't get really vanishing gradient anymore. And then the output of the last layer, we are going to have our image. And then you just simply go ahead with vanilla GAN, even not Wasserstein GAN. You just go ahead with vanilla GAN architecture, approach, and train this guy. You are going to have your output image. So this is what we got out of Big GAN, and this was quite impressive. So, given this idea, people said, okay, like the convolutional layers are doing very good, so maybe we can also use attention mechanism, because this is going to get like capture the spatial, correlations very effectively if we have so many samples of data. And then they come up by building generators which use self-attention mechanism. Now, if it comes as a question to your mind, how exactly we can use self-attention in when we are working with images, because all the examples we had here were about images, and typically GAN is a very good model for generating visual data. The point here is that if we have a set here, a tensor here, then we can generate key query value, so different values, and then they are going to be exactly the same kind of tensor. And then again, we're going to compare key and query. We're going to get attention map. This is something that we call it attention map. And then now that you have value, you're going to get the attention map. You just scale the values with the attention map, and then we do one. We can do it simply by doing the one by one convolution, and we end up with one tensor of attention values. So eventually they got this kind of mechanism. They repeated this multiple times till they get their output. I mean, of course, they use some other, fully connected processes, layers somewhere to just, match the dimension and things like that. But at the end of the day, the major part was this self-attention. And using that, if you train it, it doesn't matter, as I said, vanilla or Wasserstein, but in the original, many of those original works, they still stuck to the original vanilla one, because that was like a kind of, like a kind of benchmark, basic benchmark that we had. So if you do this, you're going to see like the output. Again, this kind of self-attention GAN is not a hard thing to implement. So you can do it by a fairly fine computation resource. And this is working fine enough to give you a bunch of images which look very close to the real images. So yeah, there has been lots of other GAN architectures. Nowadays, we have even diffusion GAN. So the idea of GAN itself is a very sophisticated idea, and it gave birth to many other ideas in this domain. So even though GANs some people consider them like less state of the art right now, but they are still giving a lot of, applications, and also bring up lots of new ideas in practice. So now, to just wrap up the whole chapter of GAN architectures, first thing is regarding like the point that GAN is just an adversarial network. So anything that has this generator discriminator architecture, and they are start to play around like in a min-max form, such that one of them tries to fool the other. This is a GAN, right? This is the architecture that we have. Cool thing about them is that the sampling from them is as easy as flow-based models, right? So you essentially just need to sample your Gaussian latent, and then you just pass it through your network. The point here is, though, that you don't have direct access to the likelihood term, so you cannot compute that. And because of this, we cannot do the direct or explicit maximum likelihood. We need to do it implicitly. Now, we can either do it by minimizing the JS divergence, Jensen-Shannon divergence, and this is going to be some sort of implicit maximum likelihood estimation, and this is what we do eventually in vanilla again. So we just solve this vanilla min-max game vanilla with a very basic form, right? But we can instead implicitly minimize the Wasserstein distance between the two distribution, the output of the generator and the data distribution. In this case, is when we are doing the Wasserstein min-max optimization, right? And both of them are valid approaches for training GAN architecture. Now, as I said, GANs are really a breakthrough in the generative AI. So it's one of the first architecture which gave us the confidence that we can really generate visual scenes very effectively. And the good thing about them in practice is that they are still the state of the art. And one of the very good thing about them is that you can implement them pretty straightforward. So many people, when they deal with a new generative problem, they just think about, okay, say diffusion models are now trend, maybe we should go directly for that. Well, you need to really see whether you really need to go for diffusion models or not. If for some applications, GAN is going to do the job for you, I strongly suggest you just stick to the GAN, because at the end of the day, the whole troubles of making it stable and if you're using Wasserstein again, making the discriminator Lipschitz, at the end of the day, all of those troubles are nothing as compared to the challenges, the computational challenges you have inside diffusion models. So it's a very straightforward approach to implement, and any student who knows deep learning can easily implement a GAN architecture and sees some good outputs. Now, that's it regarding the GAN. And the next, as I said, GAN is the first implicit approach that we use to generate images or generate data samples. Now, the next step that we're going to land is going to be the variational autoencoder and variational inference. So this is another approach that we can implicitly try to, minimize the difference between our data distribution and model distribution. And for that, what we need to understand what is the idea of variational inference, which is a quite simple idea, but is a very useful one, which can help us develop the variational autoencoders and also diffusion models. So that's going to be the topic that we're going to study at the summer break.